We're going to continue our exponent properties here at part 2. If you didn't watch part 1 yet, make sure you go back and watch that. It's going to contain some things that we'll need for this video as well. So let's start with the 0 and negative exponents. That's the next couple things we'll look at here. Essentially x raised to a negative power versus x raised to the 0 power. And it's kind of weird what happens with these, but if you consider a table of all the possibilities here, it kind of makes sense as we watch through it here. So we know what these positive powers are, and as we make this table, let's just look at what happens to all these values in here. So first things first, let's go ahead and get what we know. 2 to the third is 8, because 2 times 2 times 2 is 8. 2 squared is 4. 2 to the first would be 2. The question is, what do you get when you do the rest of these? Let's just look at what's been happening so far in the table. From 8 to 4, well, we could get to there by dividing by 2. And that kind of makes sense, because we had 3 2's here and 2 there. So if we divide one of these out, we'll now have this answer. Same thing here. If we divide this by 2 again, we'll get from 4 to 2. And this, again, makes sense, because 2 times 2, if we divide one of these out, we're left with just 2. The weird thing is what happens next, because you can continue this pattern indefinitely. You can just keep dividing by 2 as many times as you want. What this turns into, if you kept going, is 1. So as strange as it seems, anything to the 0 is 1, except 0 to the 0. That's technically undefined, so that one we won't worry about. But anything else, it's a regular number, raised to the 0 will just become normal 1. So we can continue this as well. If we kept going, you could just keep dividing by 2. 1 over 2 is a half. Divide by 2 again, and we'll get 1/4. Divide by 2 again, and we'll get an 1/8. And we can try to figure out why that worked as well. If you picture 2 to the negative first turning into 1 over 2, well, technically that's 1 over 2 to the first, right? So maybe this negative power just became a positive power in the bottom of the fraction. Let's try that here. Turns out, yep, that's actually kind of right, because this is 1 over 2 squared, and this is 1 over 2 to the third. So anything with a negative power, as strange as it seems, will just essentially be flipped to the bottom of a fraction. This is a reciprocal, is the technical term for it. So x to the negative term, or negative n, would be 1 over x to the positive n. When it changes sides, you would switch it from being positive to negative, and vice versa. If you have something to the 0 power, as long as x isn't 0 itself, this will always equal 1. So a couple quick things here, just to make sure we see a difference. If you had x to the negative third, this would be 1 over x to the third. Again, you're writing it on the bottom of the fraction instead. If it was already in the bottom, like you started off here, you could then bring it to the top and write it as x to the regular third. So anything with a negative power essentially changes which half of the fraction it's on. Since this was originally over 1, and this is now over 1, it's just switching. We just usually don't write the divide by 1. So let's do a few more examples, and then we'll do the last property. The thing with this one that I see a lot is you identify the negative power, and that's good. So this is going to do something with flipping up and down on the fraction. The thing is that people tend to attach the 4 to the x when really they're just sitting next to each other with a multiplication in between. There's no reason to do anything special here other than keep the 4 in the top and now write the x in the bottom. The 4 had nothing to do with the negative power, it doesn't move. The x does, however, shift to the bottom of the fraction. And this is how you would leave it. In 2, we kind of just saw one like this. The negative power should rise to the top of the fraction, and now it's fifth. You can write it over 1 if you want to. It's just not needed, so we usually don't. But that would just be x to the fifth in its simplest form. 3 looks kind of complicated with all these different powers here, but the idea is the same. Usually what I do in a problem like this is I just give myself a big fraction bar to start with, and I start assigning things to where they would be. So first, a is a negative power, and it's currently in the top. Now it's going to be in the bottom with a positive power. B is a negative power, it's in the top, and now it's going to be in the bottom with a positive power. C is in the bottom, but it has a positive power, so it will not move. That will stay where it is. D has a negative power, and it used to be in the bottom. Now it'll be up here in the top, and this is how you would leave it. So anything with a lot of variables or a lot of different powers, I tend to just make one big fraction bar and start plugging one thing at a time in and just seeing where it shows up. If any of these matched, we could try to reduce them a little bit, but this is where we're at. In 4, this also is a mistake I see a lot with a negative number here. This negative number is not a negative exponent, so it shouldn't move. It's kind of like this 4 here. It's just not going to do anything. It's just going to sit here on the top of the fraction. This will come up to the top here. So negative 3 x to the 4th multiplied by x to the 7th, all over 1 if you want to leave it there. We can go back to a couple of things we learned before. These x's are being multiplied, they are a common base. Let's add those up, and let's say that's negative 3x to the 11th, and that's how you leave it. Okay. The last property that we'll do here is division of common bases. This one's actually pretty simple. It's like what we did before. Picture when we had x to the n multiplied by x to the m. We said, well, that's the addition of powers. We noticed that it's a lot of x's multiplied together. A very similar thing is going to happen here. So let's just actually write these out again and watch what happens. X to the 6th over x to the 4th. That technically means 6x's all multiplied together, divided by 4x's all multiplied together. And the nice thing about fractions is when you are dividing things, as long as there's multiplication linking all these like it is, you could reduce some common items here. 2 divided by 2 is equal to 1. X divided by x is equal to 1, as long as x is equal to 0. So we can reduce any common x's there and basically just make them all 1s, which doesn't do anything to the fraction. So you're really just left with these two, which would be x squared in the top over 1 if you wanted to write it, or just plain old x squared. Now, the shortcut would have been to subtract the 6 and the 4, kind of like when we added these two together. So multiplication, addition, division, and you subtract. So it'd be x to the n minus m. Now the thing that I see sometimes with this is when the bottom has a larger exponent. So for example, if I had x to the 3rd divided by x to the 5th, you would have 3x's divided by 5x's, and you would try to reduce the same way. You would cross off x's that are common, and you're left with 2 again, but in this case they're not in the top, they're in the bottom, so you would have to leave them there. And you could actually just use the property we just learned and say x to the 3rd over x to the 5th. Well, we would subtract the powers, right, and say x to the 3rd minus 5th, which is x to the negative 2, and sure enough, it's the same thing. So all these properties really go hand in hand. There's often situations you'll find yourself in where you could use any of them in any order, and it won't matter unless you make a mistake as you're going through it. So one more slide of practice here, and we'll move on from there. X to the 10th, x to the 4th, subtract those powers. X to the 6th is all we're left with. These, same thing. You can subtract those powers, and it's negative 2, or just x to the 2nd on the bottom. 3, we saw one like this in the previous example. 2 over 2, I see people write this as 1 to the 5th far too often. You're subtracting the powers, and you want to divide the 2's, but again, just think about what's happening here. This is 8 2's, and you're dividing out some of them. Some of them do become 1's. These become 1's, these become 1's, so do these. All the rest are still 2's. So it shouldn't be 1 to the 5th, it should be 2 to the 5th. And if you want, you can write that as 32. You can actually multiply it out since it's a real solid number. And had you done this right to begin with, 2 to the 8th is 256, 2 to the 3rd is 8. You can divide these right away and just get 32, but the way to do it with power properties is to use the subtraction and don't change the base, just like we did in the previous slide. Last one here, 20 over 8, x over x, y squared over y squared. The thing that I see here as well is 20 over 8. People want to subtract that now that we're getting subtracting powers. Again, 20 and 8 are not powers, they're just normal numbers. So reduce those like normal. 20 over 8, when reduced, becomes 5 over 3, or 5 over 2. So you can divide both those by 4, reduce a little bit, and then x to the 4th, subtract those powers. That's still 3x left on top. If you subtract the powers here, you get y to the 0, which is really just 1. So that doesn't even need to be written. And in picture, you can reduce these completely. All the y's are gone now. So this would be best written as 5x to the 3rd over 2. So quick recap again. We've got a couple new things here. Negative powers can be written as reciprocals. If it's already in the bottom of a fraction, bring it to the top. If it's in the top, bring it to the bottom. And you would change this to being a positive power then. Anything to the 0 is 1 other than 0 itself. And if you have division of common bases, you can subtract their powers.